So now we'll go ahead and do example 1. It reads, the annual expenditure on health in the U.S. from 1980 to 2009 increased exponentially as approximated by the model C of T equals a bunch of stuff, where C of T is in billions of dollars and T is in years since 1980. Part B, we'd actually solved part A earlier. According to the model, how fast is the annual expenditure growing? So we've already pointed out that how fast is the same thing as at what rate is the annual expenditure, since the C function is the expenditure function. That's what we're taking a derivative of. Instead of saying rate of change, this problem said how fast is it growing in 1991 because T is in years for our input. So we've determined that we have to take a derivative, but we've only been taking derivatives of exponentials where it was just a base with an exponent. But in this particular problem, we have 296 in front of the exponential. So then first, let's go ahead and remember if a derivative was 5x squared, a function was 5x squared, the derivative would be 10x. We get that from leaving the 5 coefficient and multiplying it with the derivative of x squared, which would be 2x. So we're going to have to use that same philosophy on this problem. So for the derivative of the function that has a coefficient of 296, we'll leave that 296 out front, the same way I did in the highlighted portion to the right where I left the 5 as the coefficient of my original function out front. So now I'm going to take a derivative, just like I did in the red, where I'm going to first copy the question, because remember it was exponential. Take the natural log of the base. The value 1.08 is the entire base. Take the derivative of the top, and now I can go ahead and clean this up where we tend to just rewrite pieces in a different order. Okay, so at this point, all I found is the function for how fast the expenditure is growing, but I have not addressed the fact that it's specifically for the year 1991. Now, for input, which is T, the question states that T is in years since 1980. So 1980 would mean T is 0. 1980 is 0 years past 1980. It's the same year. 1981 would be T equals 1 because it's 1 year later. So if you notice, when T is 0, the year ends in a 0. When T is 1, the year ends in a 1. But I have to be careful because 1991 is actually 11 years later. I can't just say T of 1 again. But now I have my input. I need to find C prime of 11. So as I plug that in the only spot that T was, right? T was only in the exponent. I get out my calculator, I type this in, and I get 53.115, etc. Now, the directions didn't tell me how many places to answer, but if you remember, the function C of T is in billions of dollars. So unless I want to multiply by a whole bunch of zeros or really move over the decimal a whole bunch of places, then I'm just going to go ahead and go with a whole number. But for my units, I have to remember that it's the output, which is the function in billions of dollars, by the input, which was T, but T is measured in years. So my final answer is $53 billion per year.